My name is Shirin Zaidi, and I'm going to be talking about streaming instabilities in Class 01 disks, or how to make planets earlier than we thought by sticking dust together. This work was done under the extremely helpful mentorship of Mordecai Maclow and Ugo Libroi through the City University of New York Graduate Center, the CEA Saclay, and the American Museum of Natural History. So let's get started. To break this down for you, my presentation today is going to consist of 4 parts. The problem I worked on for about 2 years, then the methodology I used to investigate it, the results of said work, and finally, the support that was necessary to make it all happen. So, to start, let's discuss the problem I took on for the master's program. To better understand the thesis question, we'll dive a little into where planets form, when they begin forming, what formation and growth barriers they encounter, and finally, how we can overcome these barriers. To acquaint you, I have an image up of a protoplanetary disk. So this is an image of HL Tau taken by the ALMA telescope. And what you're looking at, can I get this all the way? That's actually really cool. So what you're looking at is a central forming star surrounded by a disk of gas and dust, right? And our current theory of disk formation is that a large molecular cloud collapses due to self-gravity, forms a star in the center, and the rest of the material forms a flatter disk due to angular momentum. So a ton of processes are happening at this time, from small-scale local turbulence to the forming star devouring material from its surroundings. And just to give you a size of this, an idea of the scale, the dust grains in this disk are on the order of microns. Plus, modern observations show that very young protoplanetary disks already have these substructures. These gaps that you see here, quite early on. So these indicate that these are made by young and forming planets much earlier than we originally thought. So as I mentioned, planet formation is a bottom-up process. In a disk mostly populated by gas, we start with micron-sized grains, work our way up to pebbles in the millimeter range, which then grow through accretion into kilometer-sized planetesimals and eventually become big planets. Seems simple enough, right? Well, there's a growth barrier they encounter between the pebble and planetesimal stage. So recall the protoplanetary disk system I mentioned earlier. You have a hungry young star forming in the center and a disk made with gas, a fluid, and dust grains embedded within it. So the drag force of said gas makes the small dust grains drift closer into the star, so they don't last quite long enough within their orbits to actually stick and grow and make it to the planetesimal stage of their life. Luckily, I live in a post-Uden and Goodman world. This is mostly for Mordecai. So there is a proposed solution to this problem, the streaming instability. So what is the streaming instability? The streaming instability is a solution to the issue of the aerodynamic drag force of the gas on the dust grains. So to picture this, let's very literally take our disk of gas and dust here. Pretend we're taking a protoplanetary disk and looking at the edge of it, the midplane. So here the gas is the fluid represented by the colored region, and the dust grains are the black dots you see. As we can see, the dust grains have their own velocities shown in white, but as they move through the gas, they're affected by the gas and slowed down by feeling a headwind, which is the arrow you see in the opposite direction. So if these dust grains are actually able to cluster together, not stick, cluster together, maybe we can call it unionizing, then the cluster can actually act as somewhat of a large particle. Essentially, the dust grains can have a back reaction on the gas, allowing them to move at a higher velocity and outlive that radial drift that's pushing them into the star. So these clusters can also start to vacuum up other dust grains, and this continues in a runaway process and is quite useful for actually allowing them to grow. So what we did was we studied the potential for the streaming instability in young protoplanetary disks soon after their formation. So to actually get into the project and investigate the question, we had to simulate disks, of course. You'll see later that we were able to simulate them with varying parameters and to investigate whether the parameter changes would hinder or help the streaming instability kick in. And then to do so, we had to find regions that actually met the streaming instability criteria to start. So we start our simulations super, super early, before the disk even forms. Taking from planet formation theory, we start with an initial molecular cloud that has a rotation, a magnetic field, other important properties. And then the cloud collapses into a disk with a central forming star surrounded by the material. So we consider the birth of the disk at the start of the star's life. And we evolve these for about 30 kiloyears each. And to do so, we use the adaptive mesh refinement code Ramses, which allows us to be able to zoom in and out of different regions of the simulation as necessary, which is useful for studying locations of the disk that seem fruitful for dust coagulation. So after we simulated the disk formation and evolution, we had to do data analysis, which started with selecting regions of interest to study. Since our simulations aren't producing ye olde spherical disk, we actually see other structures due to mechanisms like gravitational fragmentation. So things that look like the disk are actually forming outside, but aren't actually part of our meaningful results. So we first select an initial output to study, then we apply this criteria from previous literature, which, as you can see, selects this clump that we don't really want because we don't consider it part of the disk. So then we refine our disk selection criteria, and we strategically move from the central radius out in annuli until we form a continuous disk and stop. And that's considered our disk to study. Then we move on to find regions that meet the streaming instability criteria. These criteria were a mask to our data, and we made sure to use restrictive criteria to provide conservative outcomes in our work. I'm running out of time already, so just to say, we require a high amount of dust within the gas, and we require for the dust to grow large enough to start decoupling from the gas. So our work culminated with results. That's what I was paid to do. And firstly, we were able to form disks. We had 5 different parameter sets. We started with a fiducial model, and just a heads up, this is the dust density of the disk. So we started with the fiducial model, played with the magnetic field, played with the resolution of the simulation itself, played with the turbulence of the initial simulation conditions, and played with the sink accretion threshold, which means that the central star was eating more material around it. As you can see, that's a really tiny disk. That didn't even have an opportunity to really get up there. But when we apply our streaming instability criteria, we actually find that it applies to all the simulations. You are able to find these regions in all of them. However, you can see that the weaker magnetic field presents the best annulus to be able to host the streaming instability. So streaming instability is possible within the first 30 kiloyears. However, the dust disk mask is not enough to form even one Earth. So our disks, all of them, had enough mass to form Earths. However, the regions that met the streaming instability criteria didn't even meet a single Earth mass threshold, which is not that great. But it's nice that we know that it can start as early as within 30 kiloyears of the star forming. What this means is we need longer simulations to be able to see how this evolves over time beyond that early stage, and we need higher resolution simulations to be able to see what's going on at those smaller scales. This could be a simulation effect. Lastly, science is not done in a vacuum. I have a lot of people to thank. My advisors, who are incredible, supportive, great cheerleaders, and professors. I'm eternally grateful that they gave me the chance to work on this. My mentors at CUNY, CCA, M&H, my peers here have been incredible. This is the best astrophysics community I could have asked for, and my friends and family. This is not exhaustive, but you know, they know what's going on. And yeah, thank you for your time. Questions?
Yes. So, I was going to say excellent timing. We have the full 5 minutes left for questions and answers from you the answers, questions from the audience, and also Lo is monitoring the chat if any questions come in. So far?
I have a, I guess, science question, which is you have disks and there's not enough mass, but there's a lot of stuff outside the disk. How long does it take that material to get into the disk, and do you think that can make up the difference? The answer can be.
So I actually don't know how long it would take for it to come in, but assuming that the gas disk is larger than the dust disk, the pressure will cause the dust grains to move further in, which is to be expected. That's something that I was interested in our simulations with. The regions that met the streaming instability were actually on the outer edges of the disks that we were simulating. And so I think that they probably have a better chance of survival if they coagulate outside, because by the time they come further into the disk, they're probably more likely to be engulfed if they're not actually, clustering in the region. But yeah, so I think that's a really good idea.
Here.
Yeah, so I was just wondering, so you said that there's not an Earth mass worth of stuff by the end of your simulation in the region where there was a streaming instability, but did you at least see things moving up to like the kilometer-sized, planetesimal-sized level where you could like hold them?
No. So the Savik's question was whether the material that was dust grains, whether they reached the kilometer size. And no, they did not. We just started to see them move up to the millimeter scale. It is quite an early. Oh, am I wrong?
We don't include the actual effects of the streaming instability.
Yeah. So these are the regions that I guess meet the criteria, but we're not modeling the streaming instability itself. But still, we did see growth because we account for growth and fragmentation in the simulations, and sticking. Yes. Emily. Does the mass of the protostar affect the presence of streaming instability? Yes. I think that the mass is probably really heavily tied also to the accretion. And something that I don't think we really focused on was the radiation effects of the star itself, and how that could, like ionize the fluid, the gas, which would also really change the parameters of the streaming instability, and whether the dust grains are able to even gather in a region. We have 1 minute and 30 seconds. Okay. Thank you, Emily.
This is bougie. This is crazy. Can the people hear me?
Yeah.
Okay. I don't know. Okay. You mentioned accretion. Did you play around with the accretion efficiency, like onto the protostar, and how do you think that would impact the streaming instability?
So, is that the accretion threshold for the protostar is what you're talking about? If that's what it is, we did model it with a lower accretion threshold, which means it was eating up much more of the material around it. And as you can see, that disk is so tiny. That disk did not really have a chance to form. The regions of the streaming instability, even though we apply our disk selection criteria, you can see that the regions still kind of sit almost outside of the visible edge of the disk according to the density. And so I think, so that's one thing we saw. Another thing we saw is that it wasn't able to complete an annulus around that disk. So there were just pockets of the streaming instability regions rather than rings, as you see in the weaker magnetic field simulation results. Yes?
So I'm just wondering if the dust is forming really far, if the streaming instability conditions are met, so really far away from the star, but you want to form your Earth-like planets kind of within an AU or whatever it is, what's the mechanism for getting the dust from all the way out there at 50 AU, wherever it is, all the way in? What's
Yeah, something I didn't really touch on here at all, but I did a little bit in my thesis, is that we actually mapped out the snow line, the T equals 150 Kelvin snow line for CO, I believe, from Phil Armitage's book. And from all that work done, what I think is happening is that there's probably some sort of planetary migration inward, because the snow line is actually quite far out into the disks. Yeah, sorry, I don't have the slides here, but it's quite far out. And so I think that if objects are to form beyond the snow line and then migrate inward, that makes sense along with our regions shown here. I think I'm out of time.